In this video, we are going to learn how the air-cooled chiller works. Commonly, there are two types of chillers. One is water-cooled chiller and another one is air-cooled chiller. Both do the same job. This means it lowers the temperature of the water coming from the AHU and then sends it back to the AHU. But there are some differences in the equipment of these two chillers. Both chillers consist of compressor, condenser, expansion valve, and evaporator. In water-cooled chiller, we use the water from the cooling tower to reduce the temperature of the refrigerant. But in air-cooled chiller, we reduce the temperature of refrigerant by using fan motor. That is the difference between the two. Now, let's see how air-cooled chiller works. Before that, we have already explained the working principle of water-cooled chiller in our channel. The link for that video is in the description. Those who need it, watch that video as well. As we have already said, there are 5 important equipment in air-cooled chiller. They are compressor, condenser, condenser fan motor, expansion valve, and evaporator. First, let's start from evaporator. An evaporator works like a heat exchanger. Shell and tube evaporator are generally used in chillers. Shell and tube evaporator means that the outside of the evaporator is like a shell and inside it is coils. Inside the coil, the water from the AHU travels. Refrigerant is around the coil. The refrigerant around the coil is very cold. Being well cooled, its cooling goes to the water inside the coil. At the same time, the heat in the water goes to the refrigerant. As the heat is exchanged between water and refrigerant, we call the evaporator a heat exchanger. The boiling point of refrigerant is very low. That means refrigerant starts boiling at very low temperature. As the heat of the water is transferred to the refrigerant starts boiling and becomes vapor. After turning into vapor, it goes to the condenser through the compressor. The water inside the coil is thoroughly cooled and again goes to the AHU. This is the process that takes place inside the evaporator. Now let's see what compressor does. After the refrigerant turns into a vapor inside the evaporator, the compressor sends all that vapor to the condenser. The compressor compresses the refrigerant well while sending it to the condenser. Due to this, the temperature and pressure of the refrigerant will become very high. Now let's see what happens inside the condenser. Condenser has coils and fan motor. All those coils are in V shape, like this. Above that, there will be fan motors. Refrigerant that coming from the compressor next travels inside the condenser coil. While traveling inside the coil, the fan motors above the condenser coil continue to blow air through the coil. At this time, the air passing through the coil removes the heat of the refrigerant that traveling inside the coil. Due to this, the temperature of refrigerant will decrease. The low-temperature refrigerant then goes from the condenser to the expansion valve. The heat of the refrigerant is reduced by the air in the condenser. That's why we call it air-cooled chiller. The process of expansion valve is a simple one. We have said that refrigerant comes at high temperature and high pressure when it comes from the compressor. The temperature of the refrigerant will decrease inside the condenser. So now, when it enters the expansion valve, the refrigerant comes in at high pressure and low temperature. The expansion valve expands refrigerant by spraying it. This will reduce the pressure of refrigerant. That is, the refrigerant that comes inside the expansion valve at high pressure is sprayed when it is sent out. Due to this, the pressure and temperature of the refrigerant will decrease. At low pressure and temperature, the refrigerant then enters the evaporator. The process starts again in the evaporator. It continues like a cycle. This is the working principle of the air-cooled chiller. In this video, we are going to discuss about the working principle of the chiller. we can see chillers in the large buildings. And there are many types of chillers. But there are commonly two types of chillers. One is air-cooled chiller and another one is water-cooled chiller. Although there are many types of chillers, they all have the same components and same working principle. Now, let's see the main components of the chiller. Compressor, condenser, evaporator, and expansion valve. Compressor. Compressor is an important component in chiller. This is used to make the refrigerant flow throughout the chiller. Commonly, there are four types of compressors. They are centrifugal compressor, screw compressor, scroll compressor, and reciprocating compressor. Next, condenser. The important job of the condenser is to reduce the temperature of the refrigerant entering it. In water-cooled chiller, we use water to reduce the temperature of the refrigerant. In air-cooled chiller, we use air to reduce the temperature of the refrigerant. Next, expansion valve. Its function is simple one. It reduces the pressure and temperature of the refrigerant by expanding the refrigerant coming from the condenser at high pressure. There are four types of expansion valve. Thermal expansion valve, pilot-operated thermal expansion valve, the electronic expansion valve, and fixed orifice expansion valve. Last, evaporator. The evaporator reduces the temperature of the water coming from the AHU with the help of refrigerant and sent back to the AHU. Now, let's see its working principle. The compressor sends the refrigerant to the condenser from evaporator, which is in the vapor phase. The water coming from cooling tower enters the condenser at 32 degrees Celsius through the copper tubes. This water travels throughout the tube. In the condenser, refrigerant travels around the copper coils. As per the thermodynamics law, the high temperature travels towards the low temperature. So, as per the law, the heat of the refrigerant, which flows around the copper coil, will transfer to the water, which flows inside the copper coils. Because the refrigerant temperature is higher than the water temperature. So, the water temperature will increase. The water comes out from the condenser at 40 degrees Celsius. As the temperature of refrigerant decreases, it changes from vapor phase to liquid phase. Next, the refrigerant travels to the expansion valve. The expansion valve reduces the pressure and temperature of the refrigerant, which comes at high pressure and high temperature. The second role of the expansion valve is to send the required amount of the refrigerant to the evaporator. A thermal bulb from the expansion valve is connected to the outlet of the evaporator. With the help of this thermal bulb, the expansion valve sends the required amount of refrigerant to the evaporator depending on the temperature of the evaporator outlet. Next, the refrigerant will enter into the evaporator. The evaporator is also similar to the condenser. In the condenser, the water from the cooling tower enters through the coil. But in the evaporator, the water from the AHU enters through the coil. The water from the AHU will enter into the evaporator at 12 degrees Celsius and it will travel throughout the coil. The refrigerant that comes in cold from the expansion valve surrounds the coil inside the evaporator. According to the law of thermodynamics, the heat of the water will transfer to the refrigerant. Because the water temperature is higher than the refrigerant. As the heat of the water goes to the refrigerant, the water cools down and comes out of the evaporator at 6 degrees Celsius and goes to the AHU. As the temperature of the refrigerant increases, the refrigerant evaporates and goes to the condenser through the compressor. This process is continuous. Look at a typical refrigeration system. We have the compressor, the condenser, the expansion valve, and the evaporator. The condenser and the evaporator are both heat exchangers. The condenser sits outside the property, and the evaporator sits inside the room being cooled. The compressor circulates a refrigerant in the pipework, which cycles between all of these components. The expansion valve regulates the flow of refrigerant. The refrigerant is a specially designed fluid which can change between being a liquid and a gas very easily. And that's because it has a very low boiling point. For example, refrigerant R410A will boil at negative 48 degrees Celsius or negative 55 degrees Fahrenheit, although this will change with pressure. But if the refrigerant is inside a pipe within a room, and the room is at 30 degrees Celsius or 86 degrees Fahrenheit, then this will be more than enough to cause it to boil from a liquid into a vapor. So the refrigerant is entering the evaporator as a low-pressure, low-temperature liquid vapor mixture. It flows on the inside of the pipe, and at the same time, a fan is moving the ambient air of the room over the outside of the pipe. This causes the refrigerant to boil. It will absorb the heat from the air through the pipe wall, and then it evaporates. As the refrigerant evaporates, it carries away the heat. It's similar to when we boil water. The water heats up, it evaporates and turns into steam, and carries this heat away. So the air on the outside is entering hot and it's leaving cold. The refrigerant continues to travel through the evaporator, picking up more heat, which boils it further until it becomes slightly superheated. This basically means it's now completely gas and doesn't contain any droplets of liquid refrigerant. Liquid damages the compressor, so we want to ensure it can't reach the compressor. The compressor sucks in the refrigerant, which is leaving the evaporator as a low-pressure, low-temperature, slightly superheated vapor. It then squeezes this together into a much smaller space, and so the pressure increases. All the heat which was picked up in the evaporator is now contained in a much smaller volume, so the temperature will increase. This is very important, and we will see why in just a moment. But if you've ever pumped up a bicycle tire, you will notice the pump becomes hotter as it's compressing the air. The refrigerant is then pushed into the condenser, where it enters as a high-pressure, high-temperature, superheated vapor. The condenser is located outside, and the outside air might be very warm on a summer's day. As heat always flows from hot to cold, we need to ensure that the refrigerant is hotter than the outside air. Otherwise, the unwanted heat will not be able to leave the refrigerant and leave our system. A fan will help to blow ambient air over the condenser to remove this heat. So the outside air is entering warm, picking up heat, and leaving hot. As the heat is removed by the air, this causes the refrigerant to condense back into a liquid. It's a little bit like when steam hits the window on a cold day. The window is cold, so it condenses the steam from a vapor into a liquid, and then this liquid starts to run down the window. The refrigerant therefore exits as a high-pressure, medium-temperature, saturated liquid, and this heads to the expansion valve. The expansion valve needs to regulate the amount of refrigerant entering the evaporator to control this superheat. If it allows too much refrigerant to flow, it can flood the evaporator, so the refrigerant doesn't evaporate and liquid reaches the compressor and possibly destroys it. But if it lets in too little refrigerant, the system won't provide enough cooling, and so it operates inefficiently. The expansion valve regulates the refrigerant by only allowing it to pass through a small hole. This creates a large pressure difference across the valve. One side is the high-pressure liquid, the other side is almost empty. The small hole causes it to almost spray into the evaporator as a part liquid, part vapor mixture. The refrigerant will expand to try and fill the empty space on the other side, and this will cause it to drop in pressure as well as temperature. It's a little bit like spraying a deodorant can or a spray paint can. It flows through a small hole causing it to expand as a part vapor and part liquid mixture, and then we can feel the can become cooler. Now, the original method to control this was by using a fixed orifice device, and you might still find these on the back of your refrigerators. The hole within this device was a fixed size, so the entire system would simply turn on and off to meet the cooling demand. It does work, but we can't maintain a stable temperature control because the system is simply turning on and off. The next evolution was the thermostatic expansion valve. This is still widely used today, and it senses the superheat at the outlet through a bulb which is filled with another refrigerant. This other refrigerant will expand to close the valve when the superheat is too high, and it condenses to open the valve when the superheat is too low. This type of valve needs to be manually calculated and adjusted by a technician. It does work very well, but it's prone to mistakes. It also takes a long time to calculate and set up, and it is also only adjusted once per service visit, which is not ideal. It will also not allow peak performance. However, it does work very well, and these will continue to be used for many years. And so the latest evolution is to use electronic expansion valves. These use a controller to measure the exact temperature and pressure and adjust the valve position automatically in real time to ensure optimal performance and maximum system efficiency. Okay, that's it for this video, but to continue learning about HVAC and refrigeration engineering, click on one of the videos on screen now, and I'll catch you there for the next lesson. Don't forget to follow us on Facebook, Twitter, LinkedIn, Instagram. We're breaking down the vapor compression refrigeration cycle, the backbone of modern HVAC and refrigeration systems. Let's start with the 4 essential components of the cycle: compressor, condenser, expansion valve, and evaporator. The refrigerant moves through these components in a closed loop, changing pressure, temperature, and phase to move heat from one place to another. The cycle has 4 key thermodynamic processes, and we'll walk through each one using pressure enthalpy and temperature entropy diagrams to visualize energy transfer. From point 1 to 2, the refrigerant enters the compressor as a low-pressure, low-temperature saturated vapor. The compressor performs isentropic compression, raising the pressure and temperature significantly. At point 2, the refrigerant is a high-pressure, high-temperature superheated vapor. Next, condensation. From 2 to 3, the refrigerant enters the condenser, where it releases heat to the surroundings, often ambient air or cooling water. It undergoes isobaric heat rejection, condensing from vapor to liquid. By point 3, we have a high-pressure saturated liquid. Then comes the expansion process. From 3 to 4, the refrigerant passes through an expansion valve or throttle. This is an isenthalpic process. The enthalpy remains constant, but pressure drops sharply. As a result, part of the liquid flashes into vapor, cooling the mixture. At point 4, we have a low-pressure liquid-vapor mix ready to absorb heat. From 4 to 1, the refrigerant enters the evaporator, where it absorbs heat from the environment or the space being cooled. This is another isobaric process, but this time it's heat absorption. The liquid completely vaporizes, and by point 1, we are back to low-pressure vapor, ready to start the cycle again. So in summary, compression increases pressure and temperature. Condensation removes heat at constant pressure. Expansion drops pressure and temperature without changing enthalpy. Evaporation absorbs heat, turning liquid into vapor, and the cycle repeats. Now let's talk applications. The vapor compression cycle has 2 primary applications. First, cooling mode. The system absorbs heat from the indoor environment and rejects it to the outside. This is the basic principle behind air conditioners and refrigerators. Second, heating mode or heat pump. The cycle is reversed. the system absorbs heat from the outdoor air and releases it indoors, even when the outside temperature is low. Both functions rely on the exact same cycle, just run in opposite directions. Most modern systems can switch between the cooling mode and heat pump mode, but how do they do that? The answer is with reversing valve, the four-way valve installed near the compressor. In cooling mode, it directs hot and high-pressure refrigerant from the compressor to the outdoor coil, turning it into a condenser. In heating mode, it reroutes the flow so that the indoor coil becomes the condenser and the outdoor coil becomes the evaporator. This single component allows the system to flip its function with the push of the thermostat setting. Let's look at how we measure the efficiency of the vapor compression cycle. The coefficient of performance, or COP, is a key metric. For cooling, it is defined as the amount of heat removed from the low temperature environment divided by the work input to the compressor. Another commonly used efficiency metric is the energy efficiency ratio, or EER. EER is defined as the cooling output in BTU per hour divided by the electrical power input in watts. For heating mode, the COP is defined as the amount of heat delivered to the high temperature environment divided by the work input to the compressor. EER uses imperial units while COP is dimensionless. A well-optimized system maximizes the heat absorption while minimizing the work input. In other words, a high COP or EER means a more efficient system. In practice, the choice of refrigerant, compressor type, and heat exchanger design all affect the system performance and environmental impacts. In theory, the vapor compression cycle follows a clean, ideal path on thermodynamic diagrams. But in practice, the actual cycle deviates from the ideal, primarily due to irreversibilities like pressure drop associated with fluid flow through the pipes and system components, and heat transfer to or from the surroundings. These effects reduce the system's overall efficiency and shift the cycle path away from the ideal curves on pH or TS diagrams. Understanding the refrigeration cycle is essential for HEC engineers as it allows them to evaluate the system performance across different operating conditions and application. Whether you're sizing chillers, analyzing HVAC loads, or selecting refrigerants, this cycle is at the core of it all. In this video, we are going to understand how a heat pump works. A heat pump operates based on the normal refrigeration cycle concept. However, a heat pump can be used for both cooling and heating purposes. The same unit can be used for heating during winter and cooling during summer. Now, let's see how a heat pump works. As we mentioned earlier, a heat pump is essentially the same as the regular AC unit we use. It consists of an indoor unit, which is inside the house, and an outdoor unit, which is outside the house. Inside these units, there are components like the indoor coil, outdoor coil, and compressor, which are things we are already familiar with. But in addition to these, a heat pump has two extra check valves, or non-return valves, and two expansion valves. One expansion valve and one check valve are located in the indoor unit, while the other set is in the outdoor unit. Additionally, the system includes a four-way reversing valve with two inlets and two outlets. This valve contains a solenoid that switches the system between heating and cooling modes based on the thermostat settings. Cooling mode. First, let's see how the system works in cooling mode. The refrigerant at high temperature exits the compressor and enters the reversing valve. From there, it flows to the outdoor unit. In the outdoor unit, the refrigerant cools down and travels through the non-return valve to the indoor unit. And then it passes through the expansion valve. When the refrigerant passes through the expansion valve, its temperature drops significantly, providing a cooling effect as it reaches the indoor coil. The indoor fan motor then blows this cool air into the room. As the refrigerant absorbs heat from the room, its temperature rises and it returns to the compressor, completing the cycle. This process continues in a loop, allowing the heat pump to function in cooling mode. Heating mode. Now, let's see how the system works in heating mode. When the thermostat is set to heating mode, the solenoid in the reversing valve activates, switching the system to heating mode. In this mode, the refrigerant at high temperature exits the compressor, enters the reversing valve, and directly flows to the indoor unit instead of the outdoor unit. The hot refrigerant reaches the indoor coil, where the indoor fan motor blows the heat into the room, warming it. The refrigerant, now at a lower temperature, flows through the non-return valve to the outdoor unit. Before entering the outdoor coil, the refrigerant passes through the expansion valve in the outdoor unit, causing its temperature to drop significantly and turning it into a liquid. When the refrigerant enters the outdoor coil, the outdoor fan blows air over the coil. The heat from the outdoor air is absorbed by the refrigerant, increasing its temperature and evaporating it into a vapor. This vaporized refrigerant re-enters the reversing valve and flows back to the compressor, continuing the cycle. This is how the heat pump functions in heating mode. I hope this video has helped you understand how a heat pump works.